Dear colleagues, it makes a great honor of mine to introduce Edward Witten. So as we're topologists here, we all know about great physical breakthroughs, which revolutionized our topology, just to mention Witten-Reshetichin-Turayef and Degroof-Witten, and Zabrak-Witten, and many, many other invariants which appeared from great ideas of Professor Witten's work. And today, as it was scheduled, there should be Jones polynomial and Khovanov homology, everything around Lou Kaufman's birthday. But the title changed a little bit, as I see, and I'm happy to start our today's talk. Professor Edward Witten will tell us about knot invariants from gauge theory in 3, 4, or 5 dimensions. Let's welcome.
Well, thank you for the invitation, and it's a pleasure to have the opportunity to speak at this great conference. I did change the title a little, but the content is the same as what I had announced. So I'm going to be discussing relations between the sequence of theories in dimensions 2, 3, 4, and 5. In 2 dimensions, there's a model which is called the WZW model of conformal field theory. Then in 3 dimensions, we'll talk about the Jones polynomial and Chern-Simons gauge theory and related invariants. In 4 dimensions, it will be what's called n equals 4 super Yang-Mills theory, but I'll explain how that comes in. And then in 5 dimensions, we'll get a construction that leads to a categorification of the Jones polynomial, a candidate for Khovanov homology, although it hasn't yet been proved mathematically that this candidate coincides with Khovanov's. Sorry, let me turn on more light here. So Von Jones originally defined the Jones polynomial of a knot in terms of his representations of the braid group. So something that you knot theorists all know much better than most physicists do is that a knot can be built as the trace of a braid. So over here on the left of this picture, I've drawn a braid, and then we form geometrically what you might call the trace of the braid by taking all the strands at the top of the braid and gluing them to the corresponding strands at the bottom. So a knot can be made from a braid, but the same knot can be made in many, many inequivalent ways from different braids. Now, for the braid group on D strands, Jones constructed several representations that depend on a complex parameter Q. So I'll denote them as Ri, comma Q. Q is the complex parameter, and I labels one of a finite set of representations for each D. So then if B is a braid, I'll write RIQ of B for the matrix that represents this braid and the representation RIQ. So Jones's original definition of the Jones polynomial was a certain linear combination of these traces. So there were particular coefficient functions Ci of Q that Jones discovered, such that the right-hand side is an invariant of the knot. Now, everything about this formula was a bit mysterious. First, the motivation for the specific braid group representations that Jones introduced, well, they were natural braid group representations, but why they were useful for knot theory was not obvious. The particular functions Ci of Q were obscure, and since the same knot can be constructed as the trace of many different braids, it's not obvious why a knot invariant can be constructed in such a fashion anyway. Well, I first learned about all these things from Michael Atiyah in around 1987, who predicted the mystery should be unraveled by interpreting the Jones polynomial in quantum field theory. There was a very important step taken by these mathematicians. They showed that the Jones representation, what they did brought, okay, so I should say that following Jones, there were many important mathematical discoveries by Lou Kaufman and other people, found many different ways of looking at the Jones polynomial. But initially, none of them were very close to mathematical physics that I knew. What brought the Jones polynomial into a world of things that were familiar to a relativistic quantum field theorist was the work of these authors. They showed that the Jones representations of the braid group are the ones that arise when one decomposes the correlation functions of a certain two-dimensional model in conformal blocks, as originally analyzed by Knižník and Zamolodchikov. So for this lecture, it's not important to understand the details of what is the WZW model. It's a two-dimensional conformal field theory. It depends on the choice of a compact group G, usually taken to be simple, and a positive integer k. It turns out that to get the Jones polynomial, the group should be SU2, and Jones's parameter q should be e to the 2 pi I over k plus 2. The WW model has what physicists call primary fields in various representations of G. To make contact with the Jones representations of the braid group, we take the primary field phi in the two-dimensional representation of SU2. And then the WW model is a two-dimensional theory, so it can be defined in any two-manifold, but here we take the two-manifold to be simply a sphere, a Riemann surface of genus 0. And what the conformal field theory will do for you is that if you take points on the sphere, I've labeled them Z1, Z2 up to Z5 in this picture, you can define what are called correlation functions. To associate to each point, you take one of these primary fields. For us, it will be this primary field associated to the two-dimensional representation of SU2. And then the model will construct for you correlation functions that depend on the choices of the points and also the representations. Now, these functions are neither holomorphic nor anti-holomorphic, and they cannot be factored as the product of a holomorphic and an anti-holomorphic function. But Knižník and Zamolodchikov had shown that there are finite sums of products of holomorphic and anti-holomorphic functions. So these correlation functions of the WZW conformal field theory model have the type of representation I've written, a finite sum of products of holomorphic and anti-holomorphic functions. So the functions f alpha are multi-valued holomorphic functions. So for each n, we can define a vector bundle Vn over the configuration space of n distinct points on the sphere with a basis given by the f's. These are automatically flat vector bundles with the f's understood as covariantly constant sections, and their monodromies when the points move around give representations of the braid group. So these representations are actually unitary because the correlation functions of the model are single-valued. So to simplify a little bit, what Chern, Simons, and Khovanov showed was that from this construction you could get the Jones representations of the braid group. Now, as understood by physicists at the time, the WZW model is a purely two-dimensional quantum field theory with no particular connection to three dimensions. But the relation of the conformal blocks of the WZW model to the Jones representations of the braid group showed that the WZW model somehow had an unexpected relation to three dimensions. There were other clues in the same period by physicists Verlinde and Moore and Seiberg, but I won't have time to explain what they did. But you see, the WZW model was understood by physicists as a purely two-dimensional theory, but the Jones representation has to do with three dimensions. Braids naturally are objects that exist in a three-dimensional space, and likewise not invariants. So once Tsuchiya, Kania, and Khovanov showed that the conformal blocks of the WZW model are related to the Jones representations, it told us that somehow the WZW model has a relation to three dimensions. Well, in three dimensions, there actually is a quantum field theory that depends on precisely the same data as the 2D WZW model, namely a gauge group G and a non-zero integer K. The model is simply Yang-Mills theory or gauge theory in three space-time dimensions, with G now understood as the gauge group. But the action is not taken to be the usual Yang-Mills action, which would be the L2 norm of the curvature of a gauge field. Instead, the action is taken to be the Chern-Simons, what mathematicians call the Chern-Simons invariance, or the Chern-Simons function of the connection. So explicitly, assuming that we have a trivial G bundle so that the connection can be viewed as a Lie algebra valued 1 form. We have this, in that case, we would have this explicit formula for the Chern-Simons function. Now, in general, the Chern-Simons function I is only gauge invariant modulo 2 pi times an integer k. Actually, mathematicians usually divide by an extra factor of 2 pi, and then they say it's valued in R mod z. But physicists usually use the normalization I've written. In quantum theory, the action must be gauge invariant mod 2 pi times an integer, so that the argument of the Feynman path integral, which is the exponential of the action times the square root of -1, will be well defined. So k must be an integer. Now, this argument, due originally to Desert, Jakiv, Templeton, is somewhat similar to the argument showing that in the WCW model in 2 dimensions, k must be an integer. I didn't describe the WCW model in detail, but had I done so, we similarly would have a multi-valued action function, analogous to this one, and the condition that the action is well-defined mod 2 pi times an integer would force, again, the coefficient to be an integer. Now, for our purposes, in knot theory, the importance of using the Chern-Simons function rather than a standard Yang-Mills action is that the Chern-Simons function can be defined on an oriented three-manifold W with no choice of metric tensor or other structure on W beyond orientation. So therefore, formally, the Feynman path integral of this theory doesn't depend on anything except W itself. In other words, if it makes sense at all, it will give a topological invariant of W. We can also include an embedded circle K by including a Wilson loop operator. So I'll take K to be an embedded oriented circle, although there are variants actually developed by Luke Hoffman, as well as others, for unoriented circles. But if we have an oriented circle, we can take the holonomy around the circle. Physicists denote the holonomy this way. Then we take the trace of the holonomy in a representation R, and that gives a gauge invariant function of connections. So for any knot in a three-manifold, in gauge theory on that three-manifold, you take the holonomy of the connection around the knot, and then you take its trace in your favorite representation, which physicists denote this way. That gives a gauge invariant function of connections. So now we can do the same path integral as before, but inserting this function. So now formally, this depends on the knot and the representation, as well as the three-manifold W, but nothing else. I'm simplifying a bit. More careful study shows that both W and K must be framed. So what we really get are invariants of a framed three-manifold with a framed embedded knot or link. So if we take W to be simply R3, this will give us an invariant of a knot in R3. Now, I've mentioned now a model in 2 dimensions and a model in 3 dimensions. In 2 dimensions, we had the WCW model, and the main thing I told you about it was that it has these correlation functions, which can have this expansion as sums of holomorphic and anti-holomorphic functions, sums of products, which enables you to define a flat vector bundle over the configuration points space of points on, in this case, points on S2, but in general, points on any Riemann surface. On the other hand, we have gauge theory in 3 dimensions. Well, what's the connection between them? The basic relation between the 3-dimensional Chern-Simons theory and the 2-dimensional WCW model is that the space of physical states of the 3D theory is the same as the space of conformal blocks of the 2D theory. In other words, I explained in 2 dimensions how to define this space of conformal blocks. We take the correlation functions, we write them as a finite sum of products of holomorphic and anti-holomorphic functions. And the holomorphic functions that appear in that decomposition span this space of conformal blocks. For the 3D theory, we just have the following generality about quantum field theory. In general, in quantum theory or quantum field theory, we always associate a Hilbert space to a manifold of one dimension less. So for example, we take our 3D theory to be R, parameterized by the time, times sigma, where sigma is a Riemann surface in general of genus G. And then, in general, to construct the physical Hilbert space, we're supposed to take the corresponding classical phase space and quantize it. The classical phase space is simply the space of all extrema of the action on the three-manifold R times sigma. That's the definition of the phase space associated to sigma. In general, it's a symplectic manifold, and by quantizing it, we get a vector space of physical states. So as I said, the classical phase space is the space on a manifold sigma is the space of classical solutions on sigma times R. In the example of Chern-Simons theory, the condition that a connection is a critical point of the Chern-Simons function is just that it should be flat. The curvature f should vanish. So the classical phase space that has to be quantized is the moduli space of flat G bundles over sigma. That can be quantized by picking a complex structure on sigma, which then induces a Kähler structure on the moduli space of flat bundles, according to a theorem of Narasimhan and Seshadri. It actually, in this complex structure, it's also the moduli space of stable bundles. And then you find that the pre-quantum line bundle that you use in quantization is the kth power of the fundamental holomorphic line bundle over M sigma, which in appropriate context is called the determinant line bundle. And the physical Hilbert space is the space of its holomorphic sections, sometimes called non-abelian theta functions. I've drastically shortened a long story, but the point is that the answer coincides with the known and in a sense standard, although rather abstract, description of the space of conformal blocks of the WCW model on the same surface. So, in other words, the physical states of Chern-Simons theory are the conformal blocks of the WCW model. I probably learned this abstract description from Graham Siegel. Nowadays, it's widely used in a more general form in research on the geometric Langlands program. What I've said is the basic link between 2 and 3 dimensions. So the basic link, again, is that conformal blocks of the 2-dimensional theory are physical states of the 3-dimensional theory. Once you know this, it's not too hard to see why the gauge theory would give a description of the Jones representations of the braid group. For this, we replace sigma by simply R2 or CP1 in a slightly different approach. But we take the Wilson lines to be parallel. So the Wilson lines are the knots. Well, we took a knot and we took the holonomy of the gauge field along the knot. Here, instead of a knot, I'll just take straight lines at fixed points in R2, but parameterized by time. And now, quantizing in the presence of these Wilson lines, we get vector spaces, which, when you let the points vary, give precisely the Jones representations of the braid group. So with some further arguments, you can obtain a formula for the expectation value of a Wilson operator associated to a general knot. And you can show that it coincides precisely with Jones's original formula for the Jones polynomial in terms of traces. So this was the original story of gauge theory and the Jones polynomial from the late 1980s. In this presentation, the theory is really defined only for an integer k, or in other words, for q of this particular form, where k is an integer, even a positive integer. If you want a theory that's defined on an arbitrary 3-manifold W, that's the right answer. The quantum invariants of a general 3-manifold are defined when Q is a root of unity, not for arbitrary Q. But if you consider just knots in R3, you can analytically continue the knot invariant J of Q and its analogs for other groups and representations to functions of a complex variable Q. More specifically, the Jones polynomial and its generalizations, such as the Kaufman bracket, I think it's called, is a Laurent polynomial in Q, or in Q to the 1/2, which is why what Jones discovered is known as a knot polynomial. Nothing I've told you so far would indicate that it was a knot polynomial. I only claim to have a knot invariant that depends on an integer k. But after analytic continuation from k to q, this invariant actually is a Laurent polynomial, which is why it's known as a knot polynomial. Of course, the function j of q is determined by its values for such values of q, because they are Zariski dense. But this approach does not explain why, first of all, the analytic continuation exists, and secondly, why it gives a Laurent polynomial. Those facts are rather mysterious from the three-dimensional Chern-Simons point of view, but the interpretation in terms of two-dimensional conformal blocks is more clear, since these statements follow from simple properties of the connection that Knizhnik and Zamolodchikov, and then Tsuchiya and Kono used to interpret. So Knizhnik and Zamolodchikov had a connection on the space of conformal blocks, and then Tsuchiya and Kani and Kono said that the Jones representations of the braid group are the holonomies of this connection. But anyway, the connection itself is holomorphic in Q, or meromorphic in Q. So the analytic continuation is obvious from that point of view. And the fact that it's a Laurent polynomial takes a little bit more work, but it's not hard to see it from properties of this connection. So in short, there are many approaches to the Jones polynomial that make it obvious why the Jones polynomial is a polynomial, starting with von Jones's original approach, where his coefficients Ci of Q were Laurent polynomials, and his representations were defined in such a way that the traces were manifestly Laurent polynomials. So that and many other approaches manifestly gives a polynomial, but does not make topological invariance very obvious. The approach via Chern-Simons gauge theory makes topological invariance obvious, but does not directly explain why the invariants are a polynomial. Well, of course, this disappointed me, but I couldn't see what to do about it. So eventually I moved on and worked on other things. And for about 20 years, I accepted this state of affairs. But eventually, new developments, mostly involving the volume conjecture, made me look for a new explanation of why the three-dimensional Chern-Simons path integral for knots in R3 can be analytically continued away from integer values of k. It turns out that this involved a link between 3 and 4 dimensions that I think is just as interesting as the better-known link between 2 and 3 dimensions. And as I'll explain at the end of the talk, it also has a 5-dimensional cousin that leads us to a proposal for Khovanov homology. Now, before tackling Feynman integrals, I want to start with an ordinary integral in 1 dimension, and we'll discuss how to analytically continue it. So I've written a simple integral on the real line that defines an entire function of a complex parameter a. I've chosen the integral so that it clearly converges for all complex a, and is obviously an entire function of a. Now I want to improve the analogy between this integral and a Feynman path integral, so I'll derive what physicists call a Ward identity. A Ward identity is just an identity obeyed by an integral that follows by integration by parts. So in this case, 0 is the integral of d by dx of this function. And starting with that, you can deduce that z of a obeys a second-order differential equation that I've written here. So by analytically continuing the integral, I want the analytically continued integral to give another solution of this equation, of the same equation. So when we generalize the path integral, we want to preserve the Ward identity. In the case of knot invariance, the analog of the Ward identity are the Skane relations obeyed by knots. Or sorry, the Skane relations obeyed by quantum invariance of knots. From a quantum field theory point of view, they have a similar origin to this differential equation. So we're going to discuss a procedure by which you could generalize this integral, preserving the differential equation, and then we'll adapt it to the case of the Jones polynomial. Well, to generalize the original integral, we first analytically continue from x to a complex variable z equals x plus iy. We can write the original integral as an integral in the complex plane on an integration cycle that happens to be the real axis. We'll generalize the integral by considering some other integration cycle in the same integral. What sort of cycle can we use? A closed cycle is no use, as the integral will vanish by Cauchy's theorem. Nor can we let gamma have a boundary, for then the Ward identity, whose proof involved integration by parts, will fail. The only option is for gamma to run from infinity to infinity in such a way that the integral converges. So, for example, for the integral I picked, it converges near infinity. It converges on the positive and negative x-axis and also on the positive and negative y-axis. So examples of good integration cycles are cycles that start, for example, at the negative x-axis and end at the positive y-axis, or start at the negative y-axis and end at the positive x-axis, and so on. Any cycle that connects one of these four ends to another will give a good integration cycle, but they will obey one linear relation, because if you go all the way around from here to here to here to here and back, that's a boundary. So in this example, there's a three-dimensional space of integration cycles that happens because we picked a quartic polynomial. If for an nth order polynomial, there would have been an n-1 dimensional space of cycles. So the integral in any of these cycles will obey the same differential equation that we had originally. Now, I've presented this in one dimension, but it should be clear that we can treat an n-dimensional integral in the same way if f is a suitable polynomial. So if f is a polynomial in n real variables such that the integral on Rn converges, we first analytically continue from real variables xk to complex variables zk, and then we consider the same integral over a suitable cycle gamma in Cn. The properties we want for gamma are the following. It should be middle dimensional so the integral makes sense, and it should have no boundary. And the function h equals minus the real part of f should go to minus infinity along gamma so that the integral over gamma will converge. So in other words, gamma is going to be a closed but not compact cycle that goes off to infinity in such a way that the integral we want converges. So for any such gamma, we get a generalization of the original integral such that all Ward identities are obeyed, where Ward identities are the differential equations that this integral will satisfy as a function in terms of the coefficients in the polynomial. And turns out, though I won't explain all the details today, that there's a nice theory of the possible gammas given by Morse theory. And this gives a good framework for understanding analytic continuation of such integrals and their asymptotic behavior. What we want to do today is to place the Chern-Simons path integral in the same framework. Well, what was the Chern-Simons path integral? It's the exponential of I times the action. The action was this Chern-Simons function times the integer k. The k is an integer so that the exponential of I times the action is well-defined, complex number of modulus 1. And then in the Chern-Simons path integral, we integrate this over the space of all connections, an infinite dimensional space, and we divide by the volume of the gauge group, which I haven't written, which Fadeev and Popov taught us to do. Well, the integrand is the exponential of a polynomial, in this case, a polynomial in A, so we're in roughly the situation I described in finite dimensions. There's no problem formally in analytically continuing the integrand. We replace A by a complex valued connection that I'll call curly A, which is A plus I phi, where you could think of phi as, locally, this phi is a one form valued in the adjoint representation of the group. And the gauge group we replace from the compact group G to its complexification that I'll call G sub C. So if G is SU2, G sub C is SL2C, the complexification of SU2. The exponent of the path integral is a polynomial in A that can be analytically continued to the same polynomial in curly A. And, well, we would replace the space of all connections by the space UC of complex valued connections. The only catch is that the integral has to run over a middle dimensional subspace in the space of complex connections. So we have to find a subspace in the space of complex valued connections that, one, is middle dimensional, and two, has the property that the analytically continued path integral converges. So, of course, if an example of an integration cycle with the right properties is just the space of real connections. But if we take that example, we'll just get back to where we were before. Chern-Simons theory, well, the original 3D Chern-Simons theory. What we want to do is to find a new construction of integration cycles on which the same integral makes sense. How are we going to do that? Well, there's a standard construction we're going to use that produces middle dimensional cycles in fairly large generality. Let UC be any set of fields on a manifold W. Pick a manifold X of one dimension higher whose boundary is W. So if W is a circle, X could be a Riemann surface with boundary W. Then pick any elliptic differential equation on X such that the desired fields on W give local boundary values for a solution of the chosen equations. I've put any in quotes because in more detail we'll need some further conditions, but roughly speaking, we can pick any elliptic differential equation. Then we define gamma to be the subspace of fields on W consisting of boundary values of global solutions on X. This subspace is always within a finite dimensional amount of being middle dimensional, with the difference being given by an index. I'll give an example in case this wasn't completely familiar. Suppose W is a circle, and let UC be the space of complex valued scalar fields phi. Of course, one middle dimensional cycle would need to take phi to be real valued, but we want to do something else. Well, okay, here's something else we can do by hand. Make a Fourier expansion of phi, and define gamma by setting to 0 half of the Fourier components, for example, the ones with n negative. So that's a different kind of middle dimensional cycle. But we could also put this in our picture. We regard the circle W as the boundary of a unit disk X in the complex Z plane. We write Z as RE to the I theta. So we have this picture. X is a disk with boundary W. And we regard the scalar field phi on W, okay, as a mathematician, the scalar function on W, a physicist will call it a field. We regard it as boundary values of a scalar function or field on X, which we also call phi. And for our elliptic differential equation, we pick the Cauchy-Riemann equation, d phi dz bar equals 0. A general solution can be expanded in a power series in Z. So when restricted to Z equals 1, a general solution takes this form. In other words, the space of boundary values of solutions on X is the middle dimensional subspace gamma that we defined by hand at the beginning. So now going back to our problem with the complex valued connection curly A, which was A plus I phi on a 3-manifold W, we now take W to be the boundary of a 4-manifold X, and on X we consider some elliptic differential equation, P of A phi equals 0. More or less any elliptic P will do if all we want is a middle dimensional subspace gamma in the space of complex valued gauge fields. Well, if we want to get strictly a middle dimensional subspace, we should pick P so that its index vanishes. Any elliptic P will have some index and will give us a subspace that will differ by n, if n is the index, from the middle dimension. But any P of 0 index will give us a middle dimensional subspace. But P is essentially uniquely determined if we want the path integral to converge. Just as in the one-dimensional example we started with, the path integral is in danger of diverging because after analytic continuation, the integrand of the path integral has a real part that's unbounded above. So when A was a real connection, the integrand of the path integral was of modulus 1. But when we allowed A to be complex, the exponent here is a complex number that in general has a real part that is unbounded above and below. But there's an identity that saves the day. See, what's troublesome is the real part of this expression. So I'm going to write an identity for that real part. If W is the boundary of X, then the real part of the complex Chern-Simons function, well, you might want to call it the imaginary part. I have a factor of I. So I've taken the real part of I times the Chern-Simons function. Well, it's negative. So my trace is positive definite. So trace is what you might regard as the negative of the natural trace in Lie algebra theory. But anyway, my trace is positive definite. So this integral is the integral of the trace of a sum of squares. So it's positive. With the minus sign, it's negative. So we want to make the real part negative. But the dangerous real part is not equal to this negative thing only. It's also, there's another term which is strictly positive. It's the integral over x. I forgot to write the trace. It's the integral over x of the trace of the square of something, therefore positive. So the identity says that the dangerous left-hand side is not negative in general, but is negative when p equals 0, which is what we need. So it turns out that the condition p equals 0 is an elliptic differential equation, and that's essentially the differential equation we need to use. I say essentially because you could perturb p a little bit and get almost the same identity. So, well, the nicest p to use, the nicest elliptic equation to use is p equals 0 because it sets the dangerous term entirely to 0. But you could very, very slightly perturb that. And although this would not be 0, it would be dominated by this negative term. But anyway, the elegant solution is that p equals 0. Now, I know this is mostly an audience of knot theorists rather than quantum field theorists, but in an audience of quantum field theorists, we might notice something, which is that this expression, which is a sum of squares, is actually very, very closely related to the action of an important physical model in 4 dimensions, which is the maximally supersymmetric form of Yang-Mills theory or gauge theory. It's called n equals 4 super Yang-Mills theory. So, well, this slide, I've explained that for physicists, but maybe there's a little bit too much detail here for this audience. But okay, once I got this far, I realized that, well, it took a while to. Okay, this formula was very reminiscent of this n equals 4 super Yang-Mills theory. It took a while to take that relationship seriously, but eventually it became clear that one should take it seriously. A related fact is the following. The equation p equals 0, which is the one which we're going to use to get the identity, to make this dangerous real part negative. Well, the equation p equals 0 is one I'd seen before. Explicitly, the condition p equals 0 is this in terms of the gauge field and, well, f mu nu, what I've written here as f, is the curvature of the unitary connection A. But then we added an imaginary part phi. And the condition p equals 0 is this system of equations, well, which first of all is a kind of 4-dimensional analog of Hitchin's equations in 2 dimensions. But more specifically, in 4 dimensions, these are conditions that Kapustin and I had run into when we were working on applying n equals 4 super Yang-Mills theory to the geometric Langlands correspondence. So not only is this term in the equation related to this 4-dimensional gauge theory, but this one is also. So we'll soon see why this is useful, but for the moment, let's leave aside the relation to this n equals 4 super-Yang-Mills theory and just try to explain what the picture is. So W is going to be a closed-oriented three-manifold. And we want to generalize Chern-Simons theory on W in such a way that K will not have to be an integer anymore. And that will explain analytic continuation in K. So roughly speaking, for any choice of a four-manifold X whose boundary is W, we get an integration cycle for an analytically continued version of the Chern-Simons path integral on W by saying that instead of integrating over real connections, we're going to integrate over complex connections, which are boundary values of solutions of the equation P equals 0 on X. So this sentence is what I just said. We're going to pick an integration cycle U consisting of complex gauge fields in W that are boundary values of a solution of P equals 0 on X. So that gives, well, there's an index that comes in, and it's strictly middle dimensional in case X is such that the index vanishes. There actually are interesting things to say when the index doesn't vanish, but I won't say them today. Well, I will. If the index is negative, we're out of luck. But if the index is positive, that means we're a little bit above the middle dimension. And then we should read what Donaldson did. Donaldson had cohomology classes in the space of connections on a four manifold. And by using Donaldson's cohomology classes, we can restrict the cycle U to a cycle of finite codimension and cancel the index in case it's positive. So we actually can do something interesting if X is such that the index is positive, but it requires using these Donaldson cohomology classes. When the index is 0, if X is such that the index is 0, then we really do get a middle dimensional integration cycle. Now, for an integration cycle of this kind, there's never any integrality condition on K. And the reason is, you see, the Chern-Simons invariant of a connection is defined in R mod Z. But if you're given an extension of the connection over a four manifold, that resolves the indeterminacy and lets you define the invariant as a real number. Here, we're given an extension over X, over a four manifold by definition. The four manifold is X, and the extension is the one that obeys the condition P equals 0. So there are never any integrality conditions on K, so there's no problem with analytic continuation. And therefore, for this cousin of the original Chern-Simons theory, there's no problem in understanding why K can be continued away from integer values. I'm going to make things perhaps a little bit more elementary, I'm going to give a one-dimensional analog. So on the left-hand side, I've written an integral that defines a version of the Bessel function, and the integral is meant to be on a unit circle. As an integral in the unit circle, it's only defined when K is an integer. And when you integrate on the unit circle, it's manifestly an entire function of T. But if you want to get away from integer K's, you can do the following. Instead of integrating on the unit circle, you can integrate on another cycle in the complex plane that I've called gamma. And then K doesn't have to be an integer, but T now has to have a positive real part. So we were able to analytically continue away from integer K, but we lost something. We no longer have an entire function. Instead, we have a function that's, well, this representation is defined for positive real T. So that's somewhat similar to the story here. When K is an integer, we didn't need X. That's analogous to integrating on the unit circle. If you want K not to be an integer, you have to pick an X. But that will cost you something. In this example, it costs you the fact that you now have to constrain T to have the positive real part. But in the gauge theory problem, what it costs you is that picking an X with boundary W will generically break some of the symmetries of W. So you will no longer have a three manifold invariant. you'll have something that's only invariant under diffeomorphisms of W that extend over X. So those of you who are familiar with quantum invariance of three manifolds know that for a generic three manifold, you really can't get away from integer k, or for the way it's usually said mathematically, you can't get away from q being a root of unity. In my language, you can't go away from integer k. But if you're willing to break some of the symmetry by picking an x, then you can get away from integer k. Now, so for general three manifold, we lost some symmetry when we by picking an x. But you can argue using Morse theory that for the special case of knots in R3, all integration cycles are equivalent. And therefore, we're going to get the ordinary Jones polynomial this way, rather than some cousin of it. And hence, this procedure explains why the Jones polynomial can be analytically continued in K. It doesn't yet explain why the Jones polynomial is a polynomial. I'll come to that in about 5 minutes, perhaps. But it does explain why the Jones polynomial can be analytically continued in K. So the standard integration cycle of Chern-Simons theory can be replaced by one for which K has no reason to be an integer. And we get a new explanation of why the Jones polynomial can be continued away from integer K. But because of the relation to Super-Yang-Mills theory, we get much more. So as I said when I mentioned my work with Kapustin, the equation P equals 0 is an equation of supersymmetric localization for the four-dimensional Super-Yang-Mills theory. So what that means, the theory has a particular supercharge Q squaring to 0. If we pass to the cohomology of Q, the Feynman integral of the four-dimensional theory localizes on solutions of P equals 0. This type of localization is a generalization of Duality-Ekman Atiyah-Bott localization in equivariant cohomology, usually studied mathematically for finite dimensional integrals, but physicists study it in infinite dimensional cases. So what I've told you so far can be stated in a more physical way. Let X be a four-manifold with boundary W. Assuming X isn't flat, we pick particular couplings to preserve the supercharge Q. If X is flat, I can skip saying that. We also pick a particular boundary condition along W. With this done, the claim is that n equals 4 Super-Yang-Mills theory on X with that boundary condition gives an analytically continued version of Chern-Simons theory on W. What the statement means is that all skein relations for knots in W will be satisfied. In general, we will get a different solution of the skein relations, but any choice of X will give us functions of knots in W that obey all skein relations. I didn't want to call them invariants because they only are invariant under those diffeomorphisms of W that extend over X. In general, not all of them. But we will always get functions that obey the skein relations. So in the particular case, though, of knots in R3, because the integration cycle is essentially unique, we actually will get knot invariants. But in general, we'll get knot functions of knots that obey skein relations. By the way, the skein relations are the familiar ones from R3, which makes sense on any three manifold. The boundary condition we need to do this has a simple description in terms of branes of string theory. It arises from the D3 NS5 brane with a non-zero theta angle. But so in string theory, this boundary condition has a simple description, but in many other points of view, it's rather unusual. So from the point of view of the second order Yang-Mills equations of the underlying n equals 4 theory, it's an elliptic boundary condition that's standard in the sense that it has the standard properties of elliptic boundary conditions. It's actually an unusual type of, it's a standard elliptic boundary condition in the second order equation. But in the theory localized on solutions of P equals 0, the boundary condition becomes trivial. It just says that P is 0 along the boundary. So it looks very unusual in the twisted topological field theory. This kind of boundary condition hadn't been studied in topological field theory before I ran into it in precisely the way I've been telling you about. It has an analog in 2 dimensions related to the coisotropic branes of Kapustin and Orlov, but that interpretation hadn't yet been appreciated at that time. Now, what I've told you in going from 3 to 4 dimensions is relatively non-standard. So this business of analytically continuing the path integral and interpreting that as a 4-dimensional path integral was a little tricky, but once we get this far, we can get a lot farther with more standard arguments. First, we apply what's called electric-magnetic duality to the 4-dimensional n equals 4 theory. In string theory, this just changes a D3 NS5 system with a theta angle to a D3 D5 system still with a theta angle. In terms of gauge theory, what happens is the following. The gauge group G is replaced by the Langlands GNO dual group G-dual, or G-check. The Langlands dual group is the one Langlands introduced in number theory, and physicists GN and O introduced it in gauge theory. GN and O are Goddard, Neutz, and Olive. The Q parameter of the Jones polynomial is replaced by e to the I theta, where theta is the gauge theory theta angle. That means in the dual description, after electric-magnetic duality, a field of instanton number n is going to be weighted by e to the I n theta, which is q to the n. In terms of the bulk localization equations, nothing happens. Localization is still in solutions of p equals 0. But because of the flip in the boundary conditions from ns5 to d5, the boundary condition is completely different. It now determines an elliptic boundary condition on the equation p equals 0, but an unusual one, as explained shortly. Because the equation and boundary condition are elliptic, it makes sense, modulo compactness issues that have not been fully settled from a mathematical point of view, to count modulo signs the solutions of the equation p equals 0 that satisfy the boundary condition. If an is the number of solutions of p equals 0 with instanton number n that satisfy the boundary condition, then supersymmetric localization tells us that the partition function is just the sum of q to the n weighted by a sub n. And in case we're doing knots on R3 and the 4 manifold is just a half space in R4, this then gives a dual formula for the Jones polynomial. And this dual formula really does explain why the Jones polynomial is a polynomial. It's a Laurent polynomial in Q, or more precisely in Q to the 1/2 in the case of SU2. So to be precise, to get the Jones polynomial, the boundary 3 manifold is just R3, the 4 manifold is just R3 times R plus, where R plus is a half line. The boundary condition on the equation p equals 0 that we need here has all the general properties of an elliptic boundary condition, but it's constructed in an unusual way by requiring the fields to have a certain sort of singularity along the boundary. The fact that it's an elliptic boundary condition was, well, proved by Mazio and me in these papers and by Taubes in this paper. To just very briefly describe what the boundary condition is, pick coordinates x along the boundary w and a coordinate y normal to the boundary. Take the boundary to be at y equals 0. And let phi be phi dot dx plus phi y dy. The boundary condition, remember phi was the imaginary part of the connection. The boundary condition is defined by requiring phi to have what I call a non-pole, because it was first introduced, well, such a behavior was first introduced by Nahm in a problem in lower dimensions related to magnetic monopoles. Anyway, the boundary condition is that phi has this kind of a singularity at y equals 0. And although that might not be a familiar way to describe a boundary condition, one can show that it does have all the standard properties of an elliptic boundary condition. Finally, from this starting point, it's straightforward to categorify the Jones polynomial and to get a candidate for the Khovanov homology of a knot. What we get is closely related to work of Gukov, Vafa, and Schwartz, whose starting point was earlier work of Ugri and Vafa. There also is somewhat related perspective in recent work of Mina Akanagic. Actually, this is one of her papers, but there are more recent ones I should have cited. In terms of branes, categorification just means replacing D3, D5 by D4, D6. So, well, had we been on a 4 manifold X, well, starting with the four manifold X, the first step is to replace X by X times a circle. And that does nothing interesting from a knot theory point of view. But then you replace the circle by R. So you replace X by X times R. And that last step is categorification. So lifting the equation P equals 0 on X to an equation on X times R is essentially categorification from this point of view. It means that since we're on X times R, we'll construct a physical Hilbert space H rather than purely numerical invariants. H is Z times Z graded by instanton number N and fermion number F. The fermion number is an Atiyah-Podody-Singer eta invariant. If one decategorifies by replacing R by a circle, the natural thing to calculate is the partition function, which is a supertrace or index, and that gives back the Jones polynomial. So here we get vector spaces associated to knots. They're bigraded, and the single variable graded trace is in fact the Jones polynomial. Mathematically, without mentioning brains, what happens is the following. Remember, the Jones polynomial comes from counting solutions of an equation P equals 0. In general, the set of solutions of an equation can't be categorified. However, according to Morse theory, the set of critical points of a function on a manifold can be categorified. The categorification of the set of solutions of df equals 0 is the cohomology of M, the real cohomology. So we want the set of solutions of the equation P equals 0 to be the critical points of some functional. That's actually not true on a generic four manifold, but it's true on a four manifold of the special form W times R plus, which we use in studying the Jones polynomial. Well, it's true a little bit more generally than I've written, but certainly it's true for W times the one manifold. For such an X, the equation P equals 0 is schematically delta gamma delta phi equals 0 for some action or energy function gamma, where phi is the full set of fields that appear in the equation P equals 0. Categorification means you add another dimension, replacing X by Y equals X times R, where R is parameterized by the time t, and you introduce the gradient flow equation. Now, luckily, this equation turns out to be elliptic, so it makes sense to count its solutions, modular compactness conditions that issues that haven't been resolved from a mathematical point of view. Assuming this, we can construct an analog of fluoric homology, and this is the categorification of the Jones polynomial. Concretely, that means the following. The solutions of P equals 0 are the classical vacua. We make a Hilbert space H0 with one basis vector for each classical vacuum. The instanton number and fermion number of the classical vacua are two conserved charges N and F, giving a Z times Z grading of the Hilbert space. The physical Hilbert space is not H0, but is the cohomology of a certain differential. Physicists call it a supercharge, but mathematically it's a differential that acts on H0. It commutes with N and increases F by 1. The matrix elements of Q between different basis vectors are computed by counting gradient flow lines between different critical points, as usual in the supersymmetric approach to Morse theory. So in summary, and I apologize if I've rushed a little bit and also if I've gone over, we've discussed the relations between a chain of theories in dimensions 2, 3, 4, and 5. In 2 dimensions, we have the conformal blocks of the WZW model. In 3 dimensions, the Jones polynomial and its description by Chern-Simons theory. In 4 dimensions, n equals 4 Super-Yang-Mills theory. And in the last step, or at least the last step I know about, we go to dimension 5 and get a categorification of the Jones polynomial. Thank you for your attention.
Okay,